All right, guys, if you've made it this far, congratulations. So we are now in a section where we're talking about electrostatics. So I just want to intro the problem type for this electrostatics section. There are more electrostatics problems, but these are just the ones that we're going to cover in the next few videos, and I want to intro them before we do that. So, okay, so the problem types that you're going to see this direct calculation E-field problems, E-field calculated from Gauss's law, and then this these sort of word calculation problems, which are trivial. But it'll just be these main two here. Okay, so what is the difference between direct calculation and Gauss's law? Well, direct calculation, you can always use it, but usually it's mathematically more complicated. Gauss's law is limited when you can use it, but it's typically mathematically a lot simpler. So what we're going to look at kind of just at a high level is how to approach doing the direct calculation for E-fields from the direct calc methods, and then when you can or cannot use Gauss's law. So that's kind of the point of this video. Okay, so first off, looking at direct calculation, there are two different approaches that you can do. Sometimes it's easier to use this equation for potential or voltage and then take the gradient of the voltage, the negative gradient of the voltage, to find your E field. So the equations, just for reference what that would look like, here is an example voltage equation, and this is from a line distribution. In this section, we're going to see charged lines, charged surfaces, and charged volumes. The subscripts that you'll see for those are L, S, and V. So if you note that this is a line distribution, we have a line. So these L's here, that means that we're dealing with a line distribution, so voltage due to a charged line. This P is very important. This is charge density, which tells you how much charge is enclosed in that line. So say, for example, I have two different lines, and one has, a really high density, and one has a lower density. You can see how those would drastically affect your overall voltage or your overall E-field calculation. So just keep that in mind. That P means density. Okay, so then, so it's a little bit easier sometimes to approach it this way, but you can also just do the direct calculation for the E-field. For the direct calculation for the E-fields, and actually also sort of for voltage, you need to figure out this r minus r prime vector. And so that's always going to be the vector from the charged shape, whatever it is, line, surface, whatever, volume. Let's say this is just a little, chunk of charge. The vector from that to a point that you're given in the problem. So you're going to have to find this r minus r prime. Sometimes that can make your math a little tricky. We'll see some examples in the problems, and we'll go over how to deal with different cases of that. So one thing that I just want to point out in this equation, here, the way that it's written is a little bit confusing. This is PL as a function of r prime, so this is really just sort of PL. Sometimes you'll get problems that'll have like this is an equation, and then we're integrating, and the bounds will affect the equation, etc., kind of like what you saw in divergence and Stokes in a few problems, but this is just PL. Okay, moving on. So, okay, E-field from Gauss's law. So Gauss's law lets us do kind of a neat trick where we have, so for example, I have a charged sphere here, just for an example, and this E dot ds that you see here should be sort of familiar from the divergence theorem. So if you think about it, what this will tell us is the E-field going through a surface, or is a vector going through the surface, but it only will take into account where it's going through the surface perpendicular to the surface, right? Which is what we saw in all those divergence problems. Like we had to find a ds that was perpendicular, right? So same thing for Gauss's law, but what that means is that we can only use it to measure surfaces where the E-field is coming out perpendicular to that surface, or else we're basically going to lose pieces of that E-field. So I can draw a Gaussian surface to enclose it, and at every point on that Gaussian surface, let me just line this up right? At every point on that Gaussian surface, that E-field would be coming through right at a right angle. So I can model it so that they're all coming through in the r hat direction because of the way we model the spherical coordinate system. Okay, so just kind of background. So there are two parts of this problem usually that we have to solve where the math gets a little dicey, where you have to find this enclosed charge and then calculate the surface. And then this is essentially how you would solve for E, right? So you would integrate and find the surface, and then you basically would divide this enclosed charge, Q enclosed over E naught, which is the permittivity of free space. So you divide that by the surface. Q enclosed sometimes requires some calculation. Like I said before, you might see a charged line, you might see a charged surface, or you might see a charged volume. So that means that Q enclosed could be equal to, like, say, my surface density multiplied by the surface area, right? Or it could equal volume, charge volume density multiplied by the volume. So in this case, like if I have a sphere, it would be this. I have an equation sheet lower down that I'll point to, so you don't have to remember these, but just sort of, I just want to kind of intro it and kind of get it in your mind. Okay, then the last part for a work calculation, say we have an E field that we calculated or that we're given, and we want to know how much work it takes to move a charge through the field. Note that work is always done against the field, right? It takes work to like move in the direction, like and push against it. So work is always done in the direction of the E field. So you'd basically be given 1 point, or point 1 and point 2, and this would be that dl that you see in the equation. That's your path through the field. So we have a line that will take you through the E field, and you want to know how much work it takes to get from point A to point B. So those are kind of the problem types that you'll see with that. Okay, so let's kind of talk about when you can and cannot use Gauss's law, and we're kind of going to look at some well-known Gauss's law problems and look at doing them using Gauss's law versus doing direct calculation, so you can kind of see why it's easier. Okay, so you can use Gauss's law if all field lines are normal to the surface that you choose to enclose your charged piece. So I just kind of want to talk about what fringing is, because this is what's limiting Gauss's law. So this is just a capacitor. In this parallel plate capacitor, all of these field lines in the middle are going up, positive and negative, just normal. But on the side, these field lines are kind of wrapping around. This is what we call fringing, bending of these field lines on the edge of a charged surface. So you cannot use Gauss's law if you have fringing effects, because if you have fringing effects, it won't be normal to a surface. So for example, I can use Gauss's law if I have an infinite plane. So I have a plane kind of just seen over here, positive E and negative E direction. And to use Gauss's law, I'm drawing this box here, either on top of or below the plane, or you can kind of put it in the middle. But I just need to make sure that at each point on the surface, any field line that goes through the surface is normal to the surface. So that counts here, right? Because I don't have any field lines going through the side here, just because everything's pointing up, because this is going to infinity and this is going to infinity. So they'll always be either straight up or straight down, always, just because we're dealing with an infinite plane. I cannot, however, use Gauss's law if it's not an infinite plane, because if I enclose it, right, I'm going to have fringing on the edges, so it will cause this sort of bending effect. Sometimes you can model things as infinite planes if the area is large enough, but it's just important to note that for Gauss's law to apply, it has to be an infinite plane. So yes, Gauss, no, we can't use Gauss's law. Okay, so I just want to take a second to talk about strategies for visualizing charge behavior when you have a charged line or surface or volume. We're almost always modeling a positive charge, so charged line, charged surface, etc., charge volume. So I want you to always think back to a point charge where we have radiating field lines. So this is probably a picture that you've seen a million times before. You have two positive point charges and they're pushing against each other, and their E field lines are diverted because of that resistance in between them. So we're going to see that in our shapes as well. So for example, if you look on the right here, every little chunk of this line behaves like a point charge and just really wants to have these radial lines unless it's facing resistance from another positive point charge. Note how these field lines are sort of like pushing against each other and being diverted downwards. That's really similar to the behavior that we see here, like because we have that curved element. So we do see those lines resisting each other. So if you have trouble visualizing this, hopefully this will help, but I think it always helps to kind of imagine it as a point charge and think about stretching that point charge out and trying to force the ends towards each other and sort of how it would resist that change. So one example here, so this is a charged disk. So this is almost like a stretched out point charge here. In the middle, we see these field lines coming straight up, kind of how we saw for that charged plane, because the top of this is a plane, but we do see those fringing effects on the side there. Close to the disk in the middle, we kind of see this plane behavior, and then as we zoom out really far out, we kind of see a point charge behavior. But we can't really use Gauss's law on this, especially up close, just because we are not able to get a shape where all of those field lines would come out perpendicular to the surface of that shape. Okay, last one is a charged ring. So if we think about just a circle of positive charges, we can imagine those field lines resisting each other, and that's causing that sort of up and down resistance, these field lines that we're seeing here. Okay, one important thing about when we're asked to find the direction of an E field. So for example, you will see a problem like this likely. For an E field direction, vectors can cancel each other out. The resultant E field for a problem like this would be in the negative Y direction, because these elements will actually cancel. And even though these field lines are curved, the way that we're modeling them, we're going to have like these elements that will cancel. And we'll see that later in problems. So visualizing does help, but if you're asked to find the E field direction, it's going to be a result of the fields that do or do not cancel in the problem. Okay. Last but not least, we talked about this a little bit before, but charge density. So say for a sphere, so we have a charged volume that's a sphere, you can use Gauss for these types of problems because it will follow the rules. If you use a Gaussian surface as a sphere, you can model all of those E field lines as coming up perpendicular through that surface, and so therefore Gauss's law will apply. So it has to enclose it, and when it encloses the shape, all of the E field lines coming through the shape have to be perpendicular to the surface. So those are the rules for Gauss. I also wanted to mention one more thing. For Gauss's law, it's also a requirement that the field be uniform, and by uniform what that means is if you look at the electric field lines coming out of a surface, they would be equidistant apart, and they would have the same strength coming out. So the same vector strength and kind of the same spacing. So just keep that in mind. So the types of problems that we'll see where you can use Gauss will usually be an infinite sphere, an infinite plane, or an infinite line. There are more, but these are just sort of the ones that we're going to see for our examples here. Here are kind of some general equations that we talked about. When dealing with potential or an electric field, the charge density is important because we might be given a volumetric charge density, a surface charge density, or a line charge density. And a lot of the times for these problems, to find out our total charge, our total Q, we have to integrate over the surface or over the volume or over the line to figure out the volume, like surface area or length of charge that we have for the problem and how that affects our field. So that's a calculation piece that you're going to see in these problems. We'll also see a calculation piece of kind of finding these radiuses from the charged space to a random point that the problem picks. Okay, so just kind of some overview here. And this is sort of what I pointed out before too, finding the total charge is important. When we're given a charge density, we have to take the area that that density exists in, or length, surface area, or volume. Okay, so here's just kind of some general stuff about the work equation. We're going to use this all later, so don't get too hung up on it. I do kind of want to point one thing out at the end here is that we're going to look at just two really famous Gauss's law problems. We're not going to go in depth for these, but I just want to point out that here's an example of a problem where you can use Gauss's law, and whenever you use Gauss's law, you can also do direct calculation. This is always an option, but I just want to kind of show how Gauss's law is the same and makes it easier. Okay, so this, for example, we have infinite charged planes here. So infinite and uniformly charged for both of these. That's kind of this blue area that you see here. This is the plane. And in this case, you pick a point above the plane. And in this case, we are using a Gaussian surface, this rectangle that I kind of showed you before. So there's a rectangle on top of the plane and on the bottom. If you had a rectangle that was like symmetrical, and you tried to find the total E fields in a rectangle that went above and below the plane, they would actually cancel out, just as a note. So we just look at the top first and then the bottom separately. So in this case, kind of like what we talked about before, you find this sort of r minus r prime from the charged area to the point, right? And then you plug in, you know, your r minus r prime. We got some, you know, complicated integrals going on here from infinity to negative infinity because that's our plane. And we just sort of plug in our points and we solve. But the main takeaway here is that when we solve for this, we get this EZ component, right? And we find that it's equal to this P naught, which is also the same as PS, or just the initial surface charge density. So the surface charge density over 2 E naught is equal to the E fields, and this is EZ. And then we find that this is the same here, right? that we find that this EZ, so and this in this side they did a positive point, right? So this is above the plane in the positive Z. So they found, so just this problem only did one side but found a positive Z, but we can see that it's equal, right? That it's equal to this side here. So both methods are fine. You can do either approach. If you can use Gauss's law, it will save you a lot of time. So when you can, always it's recommended. Okay, so one more. Looking at an infinite line of charge, again, you can use direct calculation or Gauss's law. The reason why this cylinder is okay to use for this problem, because if you have a line charge, kind of what we said before when we were looking at how the point charges behave, this line charge at every point is going to radiate charge out here, and all of these E field lines are going to be perpendicular to the surface of the cylinder in the r hat direction. That's why we can use the cylinder here. And because it's infinite, right, we don't have any fringing on the sides because we're pretending that this line goes on, you know, forever to infinity and to negative infinity. That's why we can do this. If it was a finite line and it didn't go to infinity or negative infinity, we would have these fringing effects on the side and we wouldn't be able to use Gauss's law. So an infinite line is when we can use Gauss's law. So you can kind of look in the description. I will link this math down here. You can kind of follow it on your own if you're curious, but I do just want to kind of point out, just because we're running into a lot of time here. So this is the ER, so the E field in the R direction is this line charge density over 2 pi E naught R, and we see over here that this is the same thing, that the E fields in the R direction is this line charge density over 2 pi E naught R. So both ways for solving this are totally valid. As you can see on the left, it's just more mathematically complicated, and I don't even think all the steps are kind of shown to simplify here. The author just sort of skips the integral solution and kind of goes on. So yeah, that's just sort of a high-level intro. I know a lot of this won't click right away. You'll kind of need to try problems on your own, but I just sort of wanted to give you a taste for what you're going to see in this section. So when a question pops into your mind as to why something is done a certain way, maybe this can help you answer that question.